Hello and welcome to a brief tutorial on stresses and deflections in rotating disks of constant thickness. Most of this material can be referenced in a textbook titled Advanced Mechanics by Ugrel. So stresses and deflections in rotating disks are really important topics because there's such a large range of application of these ideas. For example, disks are associated with disc brakes, gas turbine engines, flywheels, gears, several manufacturing processes, including grinding wheels and cutting discs. They're also involved with disk drives. Those used to be a lot more important than they are today. But there's also electronic components and products. Some that I've been recently involved with as well is the development of hubs for UAV motors and propellers. They're spinning these UAV propellers, are sometimes called propulsors, up around 20,000 cycles per second. And when you're spinning that fast, the stresses can become very large. And so it's important that we understand what effect the speed and any initial pre-stress might have on the disk and the stresses that develop in that disk as it spins so that it doesn't come flying apart. So I think that's more of the application today is in spinning fans and propellers, things like that, compared to some of these other technologies that have been around for a while. So based on that, let's talk about developing the equations and see what they look like. The governing equations come from the same equilibrium equations that we use to develop the thick-walled cylinder equations. And this equation in polar form is given by this equation here. If you recall, in all of this, sigma r is the radial stress, sigma theta is the circumferential stress, and sigma theta actually has several names. It can be called sigma theta, sigma tangential, hoop stress, sigma t is often used. The r is the radius to the point of interest in the body, and this Fr represents body forces, and in these rotating disk problems, this will not typically drop out, but will become a significant quantity as the speed of the disk increases. So in this equation, talking about F sub r, it represents the body forces again, and in the case of a rotating disk, this can be expressed as Fr is equal to rho omega squared r, where rho is the density of the material, it's a mass density. Omega squared is the angular velocity in radians per second, and then we square that, and then r is the radius. So one thing that this equation up here does neglect when we write Fr just as this is the gravitational body force, but that's typically okay because it's usually a small component when disks are spinning fairly quickly. So using Hooke's law, sigma equals EE, these expressions for sigma r and sigma theta can be developed. E, here's the modulus of elasticity. This nu is Poisson's ratio. Use the displacement, radial displacement, and so you can see how these equations develop. Substituting these back up into equation 1, we get this differential equation, and we can solve for u by this expression. And now we need to apply boundary conditions to solve for C1 and C2. The expressions for the radial and circumferential stresses can be written as shown here. And again, like for cylinders, we see a lot of similarities in the equation, but there are a few more pronounced differences here. For example, we have 1 plus 3 nu as compared to 3 plus nu. These coefficients out here are similar, but this first term is slightly different. So there's a little more than just a plus and minus sign in these equations as compared to the expressions for the pressures in a thick-walled cylinder. The boundary conditions used to solve for C1 and C2 depend on the type of disk that we're looking at. So if we look at an annular disk, this would be a disk with a hole in the center where there would be no pressure at the inner radius and no pressure at the outer radius. So the inner radius would be given, is recognized or quantified by A. The outer radius is B. And the boundary conditions are that the radial stress at the inner wall is equal to 0, and the radial stress at the outer wall is equal to 0. And again, that's because the pressures at those points are equal to 0. So using these boundary conditions, we can come down and show that the equations for the stresses become sigma r as this expression and sigma theta as this expression, and the displacement u can be expressed as given by this equation here. So again, nu is Poisson's ratio, A is inner radius, B is outer radius, R is point of interest, rho is density of the material, and omega is the speed in radians per second. In terms of a solid disk, in this case, the inner radius is equal to 0, so this would be like a shaft. And at that point, then, the radial stress out at R equals B is equal to 0. But what we do is we say the displacement at R equals 0 is equal to 0. So these boundary conditions are a little different for the solid disk. Applying these boundary conditions, we can solve for equations 6, 7, and 8 for the radial circumferential stress equations and the displacement equations. And you can see here that these expressions for the solid disk are more simple than these equations back here for the annular disk. Plotting the stresses and displacements in the annular disk can be shown as given here in this slide. You can see that the tangential stress is largest again at the inside surface and decays non-linearly at first and then somewhat linearly. The radial stress peaks somewhere inside the disk. It's 0 at the boundaries and then peaks into the depth of the annular disk. Here, this displacement plot is kind of confusing, but the thing that you'll note is that there's very little difference between this point and this point here. But the displacements are nonlinear through there and do vary. In the solid disk, you can see that the radial stress again is lower than the tangential stress, but the radial stress is not 0 at the center of the solid disk. And our displacement is somewhat linear until we get to the outside, and then we start to become nonlinear. So again, these plots here are simply obtained by plotting these equations for the solid disk and these equations here for the annular disk. So let's talk about the design of flywheels and disks that have somewhat of an inertia to them or a press fit to them. So we say flywheel here, but this could also be the hub for a set of turbine blades or propeller blades where we're designing the hub to handle the stresses that would be applied. So it says here a flywheel is often used to even out the speed of a rotating shaft due to fluctuations in the torque or load. So if you're not familiar with what a flywheel is, the basic idea is that you get this large mass spinning, and then if you have inconsistencies in your forces or your torques or the loading, this flywheel has enough stored potential energy in it that it just keeps on rotating and helps you spin through some of those break points when maybe your torques and other things go low. So a flywheel is essentially a potential energy storing device. And they're used quite a bit. They used to be used a lot in farm equipment and vehicles, but they still have their purpose in many combustion engines and stuff where you need to store an energy to help you break through some null points, such as when your piston breaks over. So the torque carried by a press fit is given by this equation here, where if you have a press fit, you take the force multiplied by the radius, and that is the torque that can be applied without slipping on that press fit. Now in a press fit, this F is the friction force, and the friction force is the area over which it acts times by the friction coefficient times by the applied load. So my friction force F here is 2 pi A, which is the circumference of the disk, times T, which is the length of the shaft that is being analyzed. P is the press fit pressure, and then F is the coefficient of friction. So typically, a standard that is followed is that a friction coefficient of 0.15 to 0.2 for smooth finishes is what's used, and this is published by the American Gear and Manufacturing Association, AGMA. So based on this expression for the torque and this expression for the force, the torque capacity of a press fit then becomes this equation right here. And the power transmitted by the shaft is the torque times the speed. So this torque fills in here, we multiply it by the speed, and that's the power that can be transmitted by that press fit. So when we look at the combined stresses due to the flywheel spinning and an internal pressure, these are the equations that we get. So for example here, sigma R is a superposition of the press fit pressure plus the spinning disk stress. So this equation right here should look familiar to you from when we talked about press fits and thick-walled cylinders and stresses in thick-walled cylinders. That's this equation here. Then this is the radial stress equation that we just developed for a spinning disk. If you come back to look at our notes here, that equation comes from this annulus equation 3 right here. And when we look at sigma theta, the second half of the sigma theta equation will come from this equation 4 on page 2. So those stresses can be computed using these equations. The overall displacement can be computed by similar ideas as superposition, where we have here the displacement due to the press fit, and then here we have the displacement due to the spinning. Now, if you recall, this distortion energy failure theory is based on all three principal stresses. And these are two of the three principal stresses. Typically in these types of problems, sigma z is 0. And so computing the distortional energy failure theory, or using the distortional energy failure theory, and computing a sigma prime can be done by computing sigma r and sigma theta. And when doing that, we can rearrange these curves and get a sigma theta max as given by this equation right here. And you can see how this is developed. It's computed at r equals a, so the inside surface, a 0 internal pressure and an external pressure P. This is the maximum circumferential stress that we would get. If we want to compute the stresses and displacement on the shaft, we can use these equations 13 here. We note that the radial and the circumferential stresses are equal on the shaft, and they're equal to the negative of the pressure, and the displacement is given by this equation here. ES is simply the modulus of elasticity of the shaft. Now, a really handy equation is this equation 14. This equation U represents the displacement that is required to keep the system from flying apart. So if we look at this definition, it says the contact pressure P depends on the angular speed omega. So for a given contact pressure P at angular speed omega, the required initial radial interference delta can be found from equations 11 and 13, where this is equation 13 and equation 11 is this equation here. And then in combining these equations, if we evaluate them at the radius r equals a, the required initial radial interference can be computed as this expression right here. And what this expression tells you then is the initial radial interference that you have to have so that your disk spinning at omega with a press fit pressure P will not separate and come flying apart. And so this is a really handy equation to help you determine press fit interference that you have to have. Let's look at an example problem and see how we can use some of these equations to compute some results. So in this example, we have a flat 0.5 meter outer diameter, 0.1 meter inner diameter, and 0.075 meter thick steel disc. And this disc is shrunk onto a steel shaft. So if the assembly is to run at speeds of 6,900 RPM, determine the shrinking allowance, the maximum stress when not rotating, and the maximum stress when rotating. And then the shaft and flywheel are made of the same material with this density, modulus of elasticity, and Poisson's ratio. So now we need to think about how we are going to approach this problem. So the way we want to do this is we want to compute the deflection in the disc and the deflection in the shaft, and then take the difference between those, and that will be the interference that we will need to have. So using equation 5, a couple pages back, we know the displacement in the disc is given by this expression here, and we note that this one is the function of the speed. So I can compute the deflection, the radial deflection in the disc, and then I can compute the deflection in the shaft as given by this expression here, which is equation 8 on previous pages. And I get these values here after plugging in the number. Note that they are a coefficient out here and then rho omega squared over E. So the interference will be given by the deflection in the disk, UD, minus the deflection in the shaft, US. And computing that then gives me a delta. So I take the 0026 minus the 2.1875 e to the minus 5. I substitute in my rho omega squared over E. And this then becomes the radial interference that I need to have in order to make this system work. Now I'm going to look at just the press fit. So here is just looking at the stresses due to the press fit and seeing what the magnitudes of those would be. So here I know my deflection equation. I can compute the pressure required to compute that deflection that I just determined. And that pressure then is given by 100.8 megapascals. So this P here is the pressure required to create this deflection. So this is my interference pressure. This is the pressure that I want to have at the interference. so that I can get this deflection, and that deflection will keep my system in contact. So based on this pressure, the maximum tangential stress can be determined, and it is computed to be 109.2 megapascals. So the sigma theta max is given by at the inside radius of the disk, and it's computed to be 109.2 megapascals. Now if we want to look at the effect that the rotation has on the press fit, that's what we're going to do down here. So to determine the maximum tangential stress when the flywheel is rotating, we're going to use superposition of the press fit stress, the stress up here, and the stress due to the rotation. Now, one thing we want to look at is the different speeds at which this can rotate, because the faster it rotates, the less stress we're going to have on the inner hub. We could actually spin it fast enough that the press fit stress becomes zero and the thing flies apart. And typically you don't want that to happen. The best way to analyze this type of a stress situation is to use MATLAB and make plots as a function of the speed. And typically, since omega squared is used in the equations, we plot the results as a function of omega squared. So to illustrate how we do this, we first compute the deflection at the maximum rotational speed of 6,900 RPM. Then we'll use that value as the interference needed in the press fit. So that if we were to spin this disk right at 6,900 RPM, we would just about be coming loose from the shaft. That's not typically how you do it in practice. You'd have a safety factor in there, but that's what we'll use in this example so that we have a number to go from. So using this as the maximum deflection, we can compute the interference pressure and then the initial press fit stress. And that's kind of what we were doing up here. Then we can compute the stress due to the rotation and add the quantities together to get the total stress. So as the disk increases in speed, we will compute a new delta for the press fit and a new total stress. And if we look at the MATLAB code that I put together to do this, it seems like it might be kind of complex, but it's actually fairly short code in that most of this code here is explaining what's going on and annotated well so that you can understand the different parts of it. So here in the first part, we just define our dimensions of our system. Here's our speed, and we're going to go from 0 to 6,900. We need to compute or convert that to an omega. So here our speed is given in terms of RPM, and we need to make sure that that's in terms of omega. So we'll go through this computation. Material properties. The first thing we want to do then is compute the displacement due to the rotation at 6,900 RPM. And that's where we can go use this expression here that starts with 3 plus nu, and we simply compute this equation. And this again is the displacement due to the rotation. And then we can look at the initial press fit pressure without rotation. These are our thick walled equations. And then we have the initial press fit stress with no rotation. And then we look at the displacement, the radial deflection, and we're going to look at a total, and this is going to be equal to the press fit delta at a zero velocity or a zero speed minus the displacement due to the rotation. So we'll look at that total by the superposition of the two components, and that gives me the delta total down here. Then I can come and compute my press fit pressure and my press fit stress, and then I can plot the stresses due to the rotation, and I can come down here then and add the total tangential stress by adding the sigma rotation, which is this term, and the sigma press fit pressure, which is this term. And when we do that, this is the plot that we get. It's pretty interesting. The blue curve here is the rotational stress. And so you can see that as our RPM is 0, our stress due to spinning the disk is 0, but as it increases, this becomes the dominant component. We have a press fit pressure that starts out as the maximum pressure at 0 RPM, but as we increase the speed of the disk, this press fit pressure decays and goes to 0. It's kind of interesting to note that these are linear in this plot. And then the total stress starts out at the maximum and is kind of a combined stress of these two equations. And so you can see that the maximum stress certainly occurs out at the end where I'm spinning at a high speed and I have a press fit pressure that is superimposed on top of that to give me the total pressure. So hopefully this, or excuse me, the total stress. So hopefully this example gives you an indication of how to use some of these equations and how to piece together some of this analysis. The next example is a flywheel assembly example. And because we're only looking at a kind of a survey of this, we will not go through this example and through this detail, but we'll kind of summarize our analysis with this problem here. And I'd want you to be able to work a problem similar to this, given these equations, and be able to understand the different deflections, understand the different equations for the stresses, and how to combine them and put them together to compute some total displacements and total stresses. So hopefully this has been helpful. We can certainly talk about this more in a review and in class. Thank you.